This video gives an overview and status of the Assumptions of Physics project as of December 2023. Usually throughout the year, students come and ask me more about the project and try to find a way to contribute. And so I usually give them this type of overview with them. So I thought I would record it to save time and also put it available online. So maybe it is interesting to other people. It's really a rough overview. The project is vast, so I'm gonna only be able to mention result and current thinking. And if there is a video that goes more in detail, it will appear in your top right corner. And if there is some areas that you would like to learn more and you want me to make a video about that, you can also leave a comment. If you're just interested in a very brief overview instead, you can just watch this video, which is the channel introduction. That sort of gives you already an idea. So let's get started. The main idea of the project, the main goal of the project is to identify a handful of physical starting points from which the basic laws can be rigorously derived. If you're familiar with modern theories like quantum mechanics, quantum field theory, and even parts of general relativity, the starting point is really a set of mathematical equation, a mathematical framework, and it's typically difficult to understand exactly what's the physical context of this mathematics, and which sort of creates problems. And so we want to sort of do things a little bit like we used to for the laws of mechanics or the laws of thermodynamics, start from physically motivated and physically justified ideas. So for example, we find that one of the assumptions that is key for classical mechanics is the idea of infinitesimal reducibility. The idea is that our system is made of parts, and so on, and studying the whole system is equivalent to studying the whole part. And under these assumptions, basically the idea is that you recover classical mechanics and classical phase space. On the other side, quantum mechanics instead works with the opposite assumption, that the system is irreducible, that you cannot tag parts, you cannot study parts of the system, you always study the whole system. So if you have an electron, you can't take a red marker and make a red dot on the electron and say, oh, I only scatter a photon with this part of the electron. You can't do that. And so the idea is that under the assumption, if the system satisfies the assumption of irreducibility, then you get a quantum system and Schrödinger equation and measurement postulate and so on. So that's basically the idea, the rough idea of what we want to do. One of the things that we noticed is that the issue is that if you really want to have everything spelled out from physical ideas, you also have to be careful of just assuming mathematical structure, for example, assuming the real numbers, because there are assumptions that you're making, hidden assumptions about the system. And so the idea is that you really have to go deep and reconstruct all the mathematics that we use in physical theory to be able to actually have a fully understood theory in terms of physical requirements. So for example, what we can do is argue that since science is evidence-based, all this theory must be characterized by experimentally verifiable statements that have a test, and if the test succeeds in final time, then the statement is true, and vice versa. And under this assumption, with a little bit of construction, you study the logic of this verifiable statement of experimental verifiability, and you're able to recover topologies and sigma algebra, which are the foundational structures on which we build the differential geometry, probability, measure theory, information theory, and every other thing. So this is sort of the overall idea of the project, the overall goal. And so this should tell you that this is we have a different approach to the foundations of physics. We're not trying to construct interpretation of quantum mechanics. We're not trying to find a theory of everything for which all the other theories are approximation. We really want to find a set of general principles and requirements that all theory must satisfy to be able to actually be physical theory, because they have to be connected to experiments. And then this gives us some sort of general mathematical framework of which all the other different theories are an instantiation. This is sort of the idea, like in like you have in mathematics, that set theory, right, is general, and everything that is invalid in set theory is valid in all the other theories, because those are just different specializations. So any other mathematical structure is a set with some additional structure. So everything that was valid for set is valid for that. So if you study group theory, if you study topological spaces, then everything that you had in defined in set theory is still valid, and so this foundational layer can be used as a common currency in all the mathematical theories, and so we want to have something like that for physics as well. And just to give you some sort of perspective from which we come from, that sort of allows us to do this, is that a lot of people that are working on foundation of physics, especially in the idea of theories of everything, they try to think about essentially what are the constituents, the objective constituents that exist apart from us, and we can call that the metaphysical reality, and it's sort of the study of what really exists. And we're basically saying, well, the physical reality, what is basically constituted by what can be studied experimentally in a reliable way. So it's not necessarily true that the fact that something exists, we can actually create reliable experiments to actually go and study it experimentally. So only the part that is accessible through experimentation of the part that exists in the world is the focus on science. And for us, what is really important in understanding this boundary, what are these requirements in terms of experimental variability, in terms of being able to identify systems and study them independently, because what we find is that these requirements show up in the theory themselves, right? So there are some elements of these requirements that show up in the theory, and so we should be cognizant that that's where it's coming from. And then above that, the physical theory really are idealized account of the physical reality. A lot of the time you have to sort of make an idealization step to be able to construct a formal system. And this is another part that we're really interested in the Assumptions of Physics project, is really understand how this process of abstract idealization work, how it works, and sort of be able to do it in a more precise way, so that there are no hidden assumptions in terms of that. So this is just to give you an understanding of what's in the back of our head, and to sort of give an overview of how this we sort of think how the whole final thing should work. Is that, as I said before, there should be a general theory that defines basic requirements that are valid in all physical theory. There is something that needs to connect to experiments, so there is going to be this logic of experimental verifiable statements, and this maps mathematically to topologies of sigma algebra. As I said before, these are the foundations of all other mathematical tools, differential geometry, information theory, measure theory, probability, and so on. And then we're going to have another layer that is information granularity. Now that we have all our statements and we can keep track of which one are verifiable and which are not, and how much are they verifiable, we want to keep track of how much information, how much resolution, how fine these statements are with respect to each other. So if I say I am in Italy, or if I say I'm in the United States, well, the statements I am in Italy gives you a lot more information. And so the idea is that this layer is going to be responsible for a geometrical and geometric structure, for measure theoretical structure, for information structures, for probability, and so on. So all of that is going to be encapsulated there. Then on top of that, we want to have some abstract notion of states and processes that, again, we need to understand what are the basic requirements for defining a physical system and processes on top of that. And again, the idea would be that these mathematical objects that represent these requirements are literally the same in all physical theory. And then this would give us a space of well-posed scientific theories, because we have all these basic requirements satisfied, and then within that space we further constrained by having assumptions. So we can say the state is infinitesimal reducible and we cover classical phase space, or the state is irreducible and then we cover quantum phase space, quantum state space, or we can say we can add assumptions on processes, not just on states, and we say that the system is deterministic and reversible, and then we find Hamiltonian mechanics as being the deterministic and reversible part of classical mechanics, and unitary evolution, the Schrödinger equation for quantum mechanics. So that's sort of overall the idea of what we are trying to do. We have two main techniques that we have developed to be able to sort of investigate these ideas. One is called reverse physics, and it starts with the physical law, and you try to tease out the assumptions and the principle. It's basically some sort of reverse engineering, and it's called reverse physics because in the foundation of mathematics there is a sort of a similar approach, which our approach is similar to them conceptually, but it's called reverse mathematics, that wants to recover the smallest set of axioms from which you can prove a particular theorem. And again, the idea is sort of the same, is to map the overall space of physical theory in our case and of mathematics in the other case, and find what parts are common, which subsystems are common, and which aren't. And the goal of reverse physics is really to start seeing the physics past the math, so that we can sort of start thinking more at high level and more as in a cohesive way, so that we have similar ideas and similar principles across theories. And then we have another approach that is called physical mathematics, that really starts from the bottom. It starts from scratch, and the idea is to layer each assumption and each axiom and each definition one by one with a physical justification, so that we start with the informal system, which is the description of the world, and then we put in a part of these are going to become elements in the formal system with that are going to be specified, and you have to justify why a physical object can be modeled in the formal system with those properties. And the idea is really to construct a one-to-one map between mathematical and physical objects, so that all the physical objects are there in the math, and in the math you only have things that have a physical counterpart, or if there aren't, at least you know exactly why you aren't, because maybe the mathematical representation is easier if you add things that are non-physical. So that's really the high-level idea, and now each section is going to go through some of these pieces, and you should feel free to skip ahead, forward, backwards, because it's sort of a lot of ideas sprinkled around all the videos, so that's sort of how this works. So the first thing that I want to talk about is the reverse physics approach on classical mechanics. And classical mechanics is essentially already completely done in terms of reverse physics. We know all the elements, what they are and where they come from, both mathematically and conceptually. So, and this you can find in the version of the book that has been published here in October. And again, the book is, the idea is that as we get more and more things done, the book gets expanded to sort of include all the pieces, new pieces that are there. The book is open access, so you can go and read it. It's available on the website. The book is also open source. It's in a GitHub repository, and the idea is we want to treat this project as sort of an open source project. Okay, let's go through classical mechanics really quickly. One of the first things that we have is different equivalent characterization of Hamiltonian mechanics. In the book there are 12, on these slides there are only 7. The idea is that you can look at the Hamiltonian equation and realize that for 1 degree of freedom it's equivalent to requiring that the displacement is divergenceless. That is, if you have a region, as many states go inside, flow inside the region as they flow outside. Another equivalent characterization is area conservation. If you start with an area and you move it with the flow, then that area is conserved. And then the idea is that, yes, it is a mathematical characterization, but now we can look at physical characterization. Since the area in statistical mechanics represents the state count, then area conservation means mapping one-to-one states, and therefore this tells us that the evolution is deterministic and reversible. Again, reversible with the idea of state counts. Of course, there is another notion of reversibility, is the thermodynamic reversibility, the idea that the entropy does not increase increase remains the same. And you can find that this is actually another equivalent characterization, because the entropy is the logarithm of the number of states. You can give another characterization in terms of information theory. The information gets conserved throughout the evolution. The information here is the Shannon entropy, well, actually the Gibbs Shannon entropy, because it's the one in phase space. And again, this is equivalent to requiring all the others. And another thing that is also equivalent is the uncertain conservation for a peak distribution. So if you have a peak distribution over phase space that move around, the uncertainty is characterized by the determinant of the covariant matrix. And if you want this to be conserved as the distribution goes around, then you actually get Hamiltonian mechanics. So here you really see how we're sort of taking ideas and trying to put them together from different sides. And we really think that a good understanding of the physical theory means understanding all these connections and why they're there and how they're actually the same thing. Connected to this, we have a way to understand both the physics and the geometry of the principle of least action. This is actually something that we published this year. You can find a video that goes more in the detail of that, but really roughly speaking, what you find is that since the flow of states that here is in position, momentum, and time, right? It's going to flow forward in time. The assumption of deterministic irreversibility will mean that flow is incompressible, therefore it emits a vector potential. And what you find is that the action is really the line integral of that vector potential. And the variation of the action is really the flow of the states through the surface that is the path and its variation. And requiring the variation of the action to be zero basically means requiring that this strip is always parallel, tangent to the flow, and therefore that the original evolution, the original path has to be an evolution for the system. So this is sort of basically the idea, and again the point is that we have a good understanding of this. And everything that we have a good understanding is why do we actually have phase space to begin. Right, so in classical mechanics, states are identified by position and momentum. Is that necessary? And the answer is basically yes, because if you are on the continuum, what happens is that density, entropy, and uniform distribution are not coordinate invariant, because if you change the coordinates, your entropy, your density, and so on will change. And what happens is that and the conjugate momentum, which you can imagine as an h bar multiplied by delta k, that delta k is of units of inverse of the position. And so the multiplication between your delta k or the delta p's and delta q are always of the same unit. And so the way that you count a state in phase space is actually frame invariant. So we agree that there is the same entropy, that there are the same state densities, and so on. And if you want to require the reverse, if you want to say, okay, I have a state space that it's a manifold and I want these densities and entropies to be frame independent, then what happens is that you recover the structure of phase space. So the areas are essentially the counter space for each degree of freedom, and the perpendicularity in a phase space means independence of the degree of freedom, which means that the total number of configurations given by the 2 degrees of freedom is just the product of the areas, because one degree of freedom does not constrain the other. And so this is essentially what it is. As I said, in the book, there is a lot more detail, but basically we have a good understanding of what this is. Another thing that we are able to rederive is really the Hamiltonian for massive particle under potential forces. And this requires essentially one extra assumption after our Hamiltonian assumptions, is that of kinematic equivalence, that the state can be recovered from the space-time trajectory. So if you see a trajectory in space-time, you're able to reconstruct the state. Under this assumption, you find that not only the relationship between momentum and velocity has to be invertible, but it has to be a function of position alone. It cannot be a function of momentum, otherwise you bump into a problem. And so you can write this in two parts. One part that sort of fixes the unit, and the other part that really gives you the dependence. And this, of course, depends on what coordinate, what frame you're in, what coordinates you're choosing. But the point is that you can take this is a partial differential equation, you can integrate it, and you find that momentum is mass times the velocity plus some other arbitrary function, which you can recognize as being the vector potential for the forces. You can take the velocity and put it on the other side. You get, using the Hamilton's equation, another equation. You can integrate that, and then you can find the Hamiltonian. You find really the Hamiltonian for massive particle under potential forces. So you can recognize this as being the potential for the electricity, and this is the potential for magnetism. And there is a way to do this in sort of relativistic setting as well. So again, the really interesting idea is that we not only get some general form, but we really get the equation of motion for potential forces. Another thing that we also recover is relativistic mechanics, and interestingly enough, it does not require new assumptions. In fact, you find that there are some hints of relativity even before assuming that you have space-time, a lot of things. So that potential that we talked before, the potential of the flow, actually is very tightly related to the energy-momentum covector. So you already have the idea that energy is the time component of four vectors. It's already there. And another thing that you find already in classical mechanics is a notion, sort of a related notion of antiparticles. And so you don't really need quantum field theory for that. It's already there in classical particle mechanics. And the way that you can think about it is that once time becomes a coordinate and it's no longer used as the affine parameter of the evolution, these two things are disconnected, and you have some sort of Hamilton-like equation between them. And so it can happen that the affine parameters is aligned with time, so it increases as the time goes forward, or it can be anti-aligned in time. And what happens is that these two cases can never be connected, because to be able to connect them, you would have to make something that starts here and sort of goes back, and then you're going to have problems that things are not going to be well defined anymore. So the affine parameters is basically, if it's anti-aligned with time, then you have these antiparticles. But the idea is that there's really nothing going backwards in time, because the affine parameter is unphysical. It's just some dummy variable that we use. So the real physical thing is that you can't connect particles, particle states that are forward aligned with time with one that are backward aligned. So that's basically the idea, and you can go and look more at the geometry of this. But the point is that even relativistic mechanics falls into this assumption. You don't really need to get anything else. And so, with this brief overview, these are the assumptions that we have in classical mechanics. We have infinitesimal reducibility, the idea that you can make things as small as you want, and that basically recovers the idea that the state space is a manifold. It's something that it's charted with real coordinates, all independent from each other, and so on. Then if you add the independence of the degree of freedom, you get the structure of classical phase space. And it's basically just a unit tracking. So to be able to have independent degrees of freedom, the units that define one has to be independent of the other. And of course, mathematics doesn't really talk about units, right? That's why we don't really have it in mathematical structure right now, but you can make the argument that this should be. And if you take care of this, then you do find the structure of phase space with this conjugate pair, position and momentum, with the idea that the product of these two things gives you areas that are coordinate invariants. or coordinate invariant. Then if you add the assumption of deterministic irreversibility, you get Hamiltonian mechanics. If you add the kinematic equivalence, then you get Lagrangian mechanics and the massive particles under potential forces. And so the idea is that if you look at the three formulation of classical mechanics, Newtonian mechanics, Lagrangian mechanics, and Hamiltonian mechanics, is that really true that they are equivalent? The idea is that Hamiltonian mechanics requires things to be deterministic and reversible. Newtonian mechanics requires a kinematic equivalence that just, knowing the velocity, you're able to determine the dynamic. That's why the acceleration then becomes a function of the velocity itself. And then the Lagrangian mechanics is sort of the intersection of the two. And so this gives you a good idea when one is valid, when the other is not valid. For example, if you have dissipative forces or driven system, then you can't use Hamiltonian mechanics or Lagrangian mechanics. You have to use Newtonian mechanics whenever you have some sort of open system that is exchanging some energy. Okay, so this is sort of the idea. We saw that it sort of ties in some things, and one of the things that I said before is that reverse physics wants to give us a link between this theory, and here we can find an example. So we saw that deterministic and reversible evolution somehow implies the existence of the conservation of energy, and this might come as a surprise, but then we can use a different argument to sort of show the same result. So if we assume that we have deterministic and reversible evolution, then the past and the future depend only on the state of the system, which means that the evolution does not depend on anything else. But this means that the system is isolated. Its evolution does not depend on what's inside, on the environment. Well, in this case, the first law of thermodynamics tells us that the system conserves energy. And so we basically have recovered that deterministic and reversible evolution implies conservation of energy. And so this essentially is just a stronger version of the first law of thermodynamics. So things are not as disconnected as one may think. Okay, so this concludes sort of a brief overview of classical mechanics. As I said, classical mechanics is all done. Reverse physics for thermodynamics, instead, we just have some idea. So everything that I'm presenting here is really not the start of being published work, is still at the status of ideas that we're trying to put together, and of course there is a space maybe to come and help and see if these things work. So one of the things that we have figured out and published, it's a good understanding of what the Shannon entropy is, the so-called information entropy, and the best way to characterize it is as variability. So you have a set of elements and you're asking how similar are the elements within the set, how different they are from each other. And you can find that under a really simple assumption, you recover this idea of the formula, the rho log rho, this formula for an indicator of variability. And what is important to us, which again it's starting to tease out subtle things, is that this indicator essentially works in different types of cases. You could have a statistical distribution, a probability distribution, or a credence distribution. You can apply this same tool and it would give you sort of a variability of different things, a variability of what is there, a variability of what could be there, or variability of what one believes could be there. And I have a set of video for this. They go in a lot more detail, and also we have different ways to sort of to reconstruct the actual formula and to characterize better. And again, you can look at the video and the paper. I'm not going to go through this right now. What the new things that we want to really add is what is entropy in a physical system, and why it can never decrease and it reaches a maximum of an equilibrium and so on. And so the idea is that we're going for is that instead of being the entropy, the count of states, it's going to be the count of all the possible ways that the system can evolve. And so you can imagine that you have the state of the system at time minus t minus delta t, the state of the system time t, and a future state, the future moment. And the evolution, the process will constrain only some possible paths. So if I am in this state here, I'm not going to be able to jump to this state. The process will force it, for example, to go in this state and so on. And so the idea is that if we take a particular state, we can ask how many evolution go through that particular state. And the evolution is sort of the complete description of all states at all times, sort of complete knowledge. And if we instead, constrain ourselves to one state at a particular time, there are going to be a bunch of evolution that are going to be compatible with that, and we can count these. And the idea is that if your process is deterministic, right, as two states go into the same state, once they are in the same state, they can never branch off anymore. And if the evolution is reversible instead, from one state I can reconstruct the previous state, and so of course then the evolution can branch, but they can never merge, because if they merged, you would be coming from two different states and you wouldn't be able to tell me where you came from. And so what happens is that, according to this definition, you find that this count of evolution can only increase or stay the same if the process is deterministic. And if the process is deterministic and reversible, then it has to stay the same. All the states in one time have to be found in the other time. And you can see these are sort of the same idea that we use in classical mechanics. Now, what happens if you have a process that has equilibria, then all the states will, once they reach in equilibria, they are going to stay there. And so the idea is that the number of evolution is maximized there. Then if you want independence, this measure on the evolution would become a product, and since we want the entropy to be additive, then we take the logarithm of the count of evolution, and so you have now an additive entropy. And so the idea is that this definition of the logarithm of the count of evolution, so from scratch, from nothing, tells us that the entropy is additive for independent system, and it increases or stays the same for deterministic system. It's equal if it's reversible, and if it's maximum at equilibrium. So this is sort of the idea of what we want, how we want to recover entropy. And the idea is that we want to argue that defining an evolution count is necessary in physics, because what we do in physics is essentially take a system and make it go through different processes, and we want to connect all these processes in different ways. We have this process of preparation, then we take this type of interaction or evolution, and then we take a measurement. So we want to be able to define these points in which we stitch processes together that are of the same system. And therefore, we need to be able to stitch these evolution together, and we need to be able to stitch the evolution count. So we need to know, it needs to be well defined, what is the evolution count here, so that when we do the stitching, we actually keep things same. And so, again, the idea is that this tells us that the definition that we had before not only is nice and justified and gives us the nice thing, but it's kind of necessary. It's something that you have to be able to do physics. And now, if one wanted to sort of reverse thermodynamics, right, we need to add a little bit more of assumptions. We essentially need to say, okay, all states are equilibria of some faster scale process which is independent from what we're doing. There are going to be extensive quantities and so on, right? So these type of things. And what happens is that what you're going to have is that you're going to be able to prove that there is an equation of state. You're going to be able to prove that you can write the entropy at equilibrium, which is going to be well defined, as a function of these extensive quantities. And once you have this, you can start using what is called the Gibbs approach to thermodynamics to recover sort of the standard traditional notion of beta, temperature, and all the other intensive quantities. And then you can study how the interplay between changes in energy of entropy between reservoir and mechanical systems, and then you basically recover the laws. And again, this is something that we are still working on, but that's sort of what we're going for, and there shouldn't be anything that is complicated here, so we expect all of this to work. Now, there is also a third law in thermodynamics, and there are different formulations for the third law. The one that it's most convenient for us because it's easier to understand how to recover it is the following. Every substance has a finite positive entropy, but the absolute zero of temperature, the entropy must become zero, and does so become in case of perfect crystalline substances. And now the idea is that we don't really want to have a fundamental principle with crystalline substances. So a better zero for our entropy is the idea of a null state of a null system, right? The system that is absent. And since entropy has to be additive, and since since nothing is independent from any other thing, then you can show that the thermodynamic entropy actually has to be zero, just from those requirements. Another way to see that is that if the entropy is logarithm of the count of evolution, well, doesn't really make sense to have a count of evolution that is less than 1. It has to be 1 at minimum, and so the entropy cannot be less than 0. And moreover, if you imagine a null system, right, the null system really cannot be, it has only one way to evolve. It just does nothing, and nothing is nothing. And so that's another idea of why the entropy has to be zero, or it cannot be less than 0. Another way to state this is be able to say that no state can describe a system more accurately than stating that the system is not there in the first place, right? So if we think in terms of information, right, once I say the system is not there, I give you a perfect description of the system. I told you everything you need to know, all the observables about the system, so it doesn't make sense to have some other description that has entropy lower than that in terms of information, because it can't be better specified. So the idea that really this third law is not something that that it's some sort of an accident, right? It's really a logical necessity to make this thing make sense. And so related to this, the idea that there is a zero, if one looks at classical mechanics and looks at sort of both the areas which, you know, the logarithm of the count of states and also the information entropy, the Gibbs entropy, you can see that this can actually take negative numbers, right? Because if you have a single point in phase space, right, the measure, the volume of a single point is actually 0. And so the logarithm of the volume would be the logarithm of 0, which would be minus infinity. And in fact, if you look at the laws for ideal gas, the entropy, right, as you decrease, it will go to minus infinity for 0 temperature, which again tells you that classical statistical mechanics and therefore classical mechanics is not tenable. What you can do, though, is impose a lower bound on the entropy, and if you do that, what you find is that the distribution on phase space that gives you a 0 entropy while minimizing the uncertainties are actually Gaussians, and therefore any distribution of any other state has to have a spread that is greater than that. So the product of sigma q and sigma p has to be greater than a constant. And so we like to call this the classical uncertainty principle, which again means that if you really have 0 entropy, then you can't squish your Gaussian as small as you want. You get a minimum idea. So the idea is that this kind of tells you that the uncertainty that you have in quantum mechanics can be understood as this requirement coming from the zeros law, because what happens is that quantum mechanics has already a lower bound on the entropy. If you do the entropy of a pure state, that has to be 0, and then any mixed state has to have a greater entropy. And so it already has sort of the third law is already there in quantum mechanics. It's not there in classical mechanics, and if you add it, you get an uncertainty principle. And so the idea is really that the uncertainty principle, you can understand it as a consequence of the third law, which is this idea that this principle of maximal description, no state can describe the system more accurately than stating that the system is not there in the first place. And so one of the things, so this sort of is the general set idea that we have on thermodynamics. And one of the things that this also tells us is that there is this a deep link between entropy, and because we also saw in classical mechanics that the conservation of entropy was one of the way to characterize classical Hamiltonian mechanics, and therefore given that there is this link on the bound, and that this link on the lower bound already gives us some statement of the uncertainty principle, what we would like to see if whether in quantum mechanics that's basically the only thing that quantum mechanics requires. Is basically say, okay, we have a system of states, we can make mixtures and so on, but we have a lower limit on the uncertainty, right? And this sort of connects what we said at the beginning about the irreducibility. So that's basically the irreducibility comes there. I have a minimum threshold under which I do not resolve the system. I cannot look at the system more, and that would be the zero of the entropy. So also for quantum mechanics, the situation is that we have some idea, we have some pieces done, but we don't have a write up with everything completely cohesive and completely figured out. So let's start with this idea of quantum mechanics being the product of irreducibility. If we have a classical system, we can identify parts of the system and study their evolution independently. Well, when we go in quantum mechanics, instead, we cannot access part of subsystem. The assumption at least is that, and therefore we have this irreducible object that we cannot be further discussed or analyzed. And again, this is an assumption, and particular systems will realize this assumption in different settings. So for example, if we have a proton and we are not doing a deep inelastic scattering, then the fact that it has a substructure with quarks and gluon does not affect the evolution of the system, and therefore we can have diffraction interference and all these quantum phenomena as if the proton is a single particle. But then if we go and do deep inelastic scattering, we elicit that internal structure, and then that assumption is violated, and therefore we cannot describe the proton as a single irreducible part. So again, this is the idea of the assumption. So the goal here is to at least qualitatively see how this assumption, the assumption of reducibility, leads to sort of ideas that are similar to what we, the sort of outcomes of similar to what we quantum mechanics predict. So the idea is that if we assume that the system is irreducible, then, for example, we must have a minimum uncertainty, because, again, we can't squeeze the ensemble arbitrarily. If we were able to take an electron and prepare it exactly in one point with one value of momentum, then clearly we would know what every part of the momentum is doing, right? It's doing exactly the same thing. And so we need this sort of uncertainty is there essentially because we cannot distinguish these parts. We cannot make everything work exactly in a way that we would know what every part was doing. Then, by the same token, if we must have a minimum uncertainty in terms of the state distribution, then we must have non-locality, right? Because we are going to have some distribution along the position, and if we were able to interact only with some part of the system, the one that was only in a particular region, then of course we would be violating the idea that the system is irreducible, that when we are interacting with one part, we're actually interacting with the whole. So the fact that this whole needs to be spatially distributed, it means that it's a whole that is spatially distributed, and therefore it is non-local. Then, of course, this also leads to the idea that even if there are these superluminary effects, they cannot carry information, because being able to see that information that is carried means, again, having access to the substructure of the irreducible system, which we can't, and so on. So these are sort of the idea of how this works, at least conceptually. One of the things that it's usually a problem in quantum mechanics is that you have two laws of evolution, one for measurement and one for time evolution, the Schrödinger equation, unitary evolution. And typically people want to resolve this by showing that the time evolution, the projection, what happens during a measurement is actually an instance of a time evolution. We don't particularly want to do that. What we want to do is show that there are processes, and all processes have to have a certain feature that are common to processes. The idea is that a process will take an ensemble as an input and will give us an ensemble as an output, and the process must be linear with respect to the mixture of these ensembles. And then we're going to have two different requirements for two different processes. If one assumption is that the process is deterministic and reversible, then this process will admit an inverse, at least conceptually, to be able to reconstruct the initial state. And this probability conservation and the ability to have an inverse will essentially give us unitary evolution of the Schrödinger equation. For measurement, instead, what you really want is that the process is repeatable, therefore that you, if applied twice, you get the same thing. Mathematically, this means that the process is idempotent, but we saw that it also has to be linear in probability, so now we have a process that is idempotent and linear, and this is the definition of what a projection is. And so, just for these basic assumptions of the process, you get these two different flavors of processes. Now, to resolve the idea that at the end of the day we should have only one thing, instead of trying to get from a unitary projection, from a unitary evolution projection, we can show that we can do the opposite. From projection, we can develop a unitary evolution. So the idea is that instead of thinking these as measurement, you can also think it as preparations, because every measurement is a preparation from what happens below. And so the idea is that unitary evolution is a sequence of infinitesimal preparation, or if you want, a sequence of infinitesimal measurements. So the idea, for example, if you have a spin coming in a vertical direction and you measure the horizontal projection, the horizontal component, then of course you're going to have a projection. But if you do this gradually, right, you put your polarimeters a little bit designed and do this gradually, you're going to be able to rotate your spin direction. So the idea is that you can see the unitary evolution as a sequence of infinitesimal projections. So sort of the projection is your infinitesimal time evolution, and then everything else can be constructed on top. Now, this idea gives us a very strong parallel between quantum mechanics and thermodynamics, which again allows us in principle to build a general theory. So the idea is that the eigenstates are really states that are not changed by the process. If you have the process, you give it the eigenstates remain what it is. And so we already have another word for this in physics. They are equilibria. And so every eigenstate is an equilibria of the process, and you can show that every state is an eigenstate of some unitary Hermitian operator. So all states in quantum mechanics are equilibria of some process, and you can also show that this is the case for mixed state. Even mixed states are equilibria of some process, and the eigenstate of this process are the same eigenstates of the mixed state that you use, for example, when you calculate the entropy. So the idea is that then the quantum context can be understood as different boundary condition between system and environment. So if I prepare spin up, right, then I must have some magnetic field oriented in the vertical direction, and when I'm measuring spin left or right, I will have some detector, that component that is aligned like that. So the idea is the change of context is simply a change in a boundary condition. So the transition between spin up and spin left, or spin left and spin up or down during a spin measurement can be seen as essentially the transition between different type of equilibria, like you have in statistical mechanics, where you go from a grand canonical ensemble to a canonical ensemble. So this is sort of the idea. And then in this context, then projection can really be understood as equilibration, and again as processes for which all the outputs are equilibrium equilibria of the process. This again gives us a more general idea of how of the value and importance of the entropic nature of the entropy in physical theory. In fact, one of the things that you can show is that all the geometrical structure that we have both in classical mechanics and quantum mechanics are there and exactly there to define the entropy. And so if you know how to define the entropy, you get those geometrical structure. If you know those geometrical structure, you can calculate the entropy. And so what comes back is that thermodynamics and statistical mechanics, they shouldn't really be thought as built on top of mechanics, but really mechanics is the ideal case of the thermodynamics and statistical mechanics. So the pure states that we have in classical mechanics and in quantum mechanics, the microstate, the points in phase space in quantum mechanics, and the pure states, the array in the Hilbert space for quantum mechanics, really they should be thought as the best preparation possible, and the deterministic and reversible processes should be thought as the best possible map between pure states. And so the idea is that thinking of all states, even pure states, as ensembles, the pure states being particular ensembles, help us give a more unified way of thinking, both in classical mechanics and quantum mechanics respectively, but also across theory. So for example, one of the things that we can do is compare the state of mixture in quantum mechanics, in classical discrete and in classical continuum, and you can better understand the sort of the similarity and differences between them. And the idea is that we should also be able to get a better understanding of what is the relationship between classical mechanics and quantum mechanics. So if we start in quantum mechanics, we know that the pure state, all pure states have a zero entropy, and then of course we can increase the entropy up to plus infinity in case of infinite dimensional spaces. And what's important is that the state of pure states is continuous. You can evolve continuously from one state to any other state. In classical mechanics, the discrete version, each state is zero entropy, and of course we can go to infinity if we have an infinite amount of states to create a distribution above. But as a difference between quantum mechanics, we cannot go continuously from one state to the other. The states are discrete, and the only way to evolve continuously is actually to increase the entropy. So there is one feature that is similar and one feature that is different. If we look at the classical continuum instead, a single point in phase space has zero volume and is associated with minus infinite entropy. Its cells of, let's say, unit size would be associated with zero entropy. And so you can go not to just plus infinity if you spread out the distribution, but you can approach minus infinity if you can make things that are infinitely peaked, as we saw in the classical uncertainty principle idea. And so, but what happens is that the space of zero entropy is still continuous. So you can go continuously from one thing to the other. And so what happens is that the quantum mechanics can really be understood as a hybrid between these discrete and classical continuum, that feature of both and feature of neither, let's say. And so quantum mixed states have no single decomposition in terms of pure states, right? So if I have a maximally mixed state for a spin 1/2 system, this can be achieved by equal mixture of up and down or left and right, right? So this is something that quantum mechanics has that classical mechanics does not have. But in classical mechanics, if you take a state that it's an entropy greater than zero, then you are going to have multiple decomposition, not in terms of the pure state, so that's always a single decomposition, but you can have multiple decomposition in terms of zero state, right? So The idea is that the way that this looks similar essentially is that quantum mechanics kind of look as a part, this internal part without the minus infinity. In fact, that's something that we would like to prove mathematically, is that classical mechanics is essentially the high entropy limit of quantum mechanics. That sort of, as you increase the entropy, these states in some sense that we still have to understand and well define, will look more and more classical. And so what we like to do ultimately is, one of the things that we think should be possible is recovering the space of quantum mechanics from assumptions on the ensemble. So you have a space of ensembles that the main feature is that they can be mixed, and this would essentially form a convex space, the idea that you can take two things and mix them in terms of probability. The idea of irreducibility, the thing that we come to ensembles that cannot be further refined, means that all these extreme points are not limits in the convex space, but are actually points within the convex space, and we are going to have to give them some finite entropy. Then we're going to assume that we have continuous time, so that the extreme points form a manifold, which is meaning that it's not discrete, it's something that we can go continuously from point to point. The idea that the manifold has to be frame invariant, so that we should be able to define entropy distributions and so on in a way that it's a frame invariant, then this tells us that the manifold is symplectic, with the same idea that we saw for classical mechanics. And then we are going to have an assumption of homogeneity, because all these states should be states of the same quantum system. And so, for example, all two-dimensional subspace are going to be of the same shape, and what we would find is that they have to be sphere because of the assumptions before, and because of frame environment invariance, the only sphere that is a symplectic sphere is the two-sphere. So you're basically recovering the block sphere for every two-dimensional space, and so the idea that this might be enough to recover complex projective spaces. So this would be more or less the only assumption that we would need to put in. And again, some of them are really how can I say, necessary. So the idea that ensembles can mix, that sort of by definition, and also homogeneity. If you have if the states are of the same system, you should be able to go from one to the other. They should all locally look the same. So these are sort of the idea that we would like to have. But one of the problems here is that we are not really sure exactly what is the correct mathematical structure to rederive everything in a coherent way. So quantum mechanics is all formulated in terms of Hilbert spaces, and one of the problems that we see is that Hilbert space contain a lot of unphysical things, so they may not be the correct spaces to derive them. So if I really want to physical motivation for the state space, it's most likely that Hilbert space is not going to be the space that you end up with. And what we did was a sort of a bit of reverse engineering in the mathematical definition to understand which part of the mathematical definitions are physical or not. And the definition of a Hilbert space, it's a complete inner product vector space. The inner product vector space structure, that seems to be to exactly capture measurement, probability and entropy of mixture, and superposition and statistical mixing. So that part is really necessary for quantum mechanics, and it's physically motivated, and it's there. This completeness, this idea that the Hilbert space is complete under Cauchy sequence, that seems not to be physically justified, and in fact to bring things that are physically suspect. It requires us essentially to include a unitary transformation, like finite time evolution, that can change a finite expectation to infinite expectation. So the idea is that inside the Hilbert space, you can find a unitary evolution, a Hamiltonian, for a process that takes states that have finite energy and gives them it sort of puts them infinite energy in infinite time, like something like that, or that takes the spread of momentum and takes it from finite to infinite time. And a lot of these things don't seem to be physically justified. The Schwartz space, the space of functions that go down faster than any polynomial to infinity, has much better mathematical properties, but again, it's not clear whether we can justify that, if it, how or other problems are. So this is an area that sort of still needs to be understood. But again, the idea is not really to find some completely different formulation of quantum mechanics. We would really like to sort of rederive as much as possible the formulation that we already have, because so that we can go and change all the textbooks, and at the end of the day, the formulation that we are using probably is there is some reason why it's comfortable and so on. So we should derive the things that we already have, and again, the quantum mechanics is really postulated into roughly 4 postulates. One is the states postulate, that states that rays are the states are represented by rays of complex vector rays. Vector space, and this again should be recovered by the properties of ensembles and rules of ensemble mixing. The measurement postulate should be recovered by this idea that projections are processes with equilibria, and the Born rule should be able to be recovered by the entropy of mixing and how these things work. For the composite system postulate, we already have a paper that shows that it can actually be derived by the 2 previous postulates and a sort of basic requirements of composite systems. And then there's going to be the evolution postulate, the one for the Schrödinger equation. Again, that can be recovered just by looking at deterministic and reversible evolution. So that's in a nutshell for quantum mechanics. Now, of course, there is the issue of field theories, both classical and quantum field theory, because a lot of modern theories are field theories, and of course, for example, general relativity is a field theory. We haven't really talked about that. And here the issue is that we're not sure that we have the correct math to generalize. So there are some issue on with essentially function spaces and defining measures on function spaces that sort of prevents some of these things to work well. One thing that people may not be aware is that the path integral formulation of quantum field theory, the one that is sort of used all the time, it's actually mathematician can prove that a measure that is required to define those integrals on the paths is actually not well defined, and again there's sort of a hole there on the mathematical sides, and so it's difficult to generalize something where it's not even clear exactly where we need to end up. But again, it's something that in our back of our mind we're working on. So this is in a nutshell was the whole overview for reverse physics, and now we can switch to physical mathematics. So first, let me give you an overview of what physical mathematics is and why we think we need a sort of a different approach to formal systems in physics for physical theory. So the common conceptions right now is that mathematics is used as a foundation for our physical theories, and so therefore a lot of the theories that we have are essentially stated with mathematical language, right? You have Hilbert spaces, you have Lagrangians, you have all these elements and groups and all these things. And in fact, it's a sort of a common understanding that finding a neat set of assumptions from which the whole theory can be derived is purview of mathematicians, because they have to look at this formal structure and figure out what are the correct technical ways to do it. And if you look at this in mathematical physics, at least when I did this video, there is this picture, and so there's also the idea that there is math on top, right, as these wonderful pristine things. And then from math you derive, all those things that can be used for physicists. You derive this mathematical physics, and somehow you derive an ontology, which I don't know what that means philosophically, that an ontology is derived by math, but again, the math tells you everything. And then you have this physics at the end, which is, this bastard child of math, so imperfect while math is so pure, right? And this is sort of the idea that a lot of people in the theory world has, right? The math is the correct thing. And the issue with that theory is that the mathematical content of a theory can never tell us the full physical context, that the connection to experiments that at the end of the day we need for physical theory. That's not in the math. Worst of all, the way that modern mathematics is structured is the meaning is sort of not there in the formal system anyway. David Hilbert says that mathematics is a game played according to certain simple rules with meaningless Markov papers. And Bertrand Russell, who also worked a lot in the foundation of mathematics, he says that it is essential not to discuss whether the first proposition of a formal system is really true, and not to mention what the anything is of which it is supposed to be true. So one of the ways that mathematics has become precise from a mathematical point of view is essentially to strip away meaning and to just talk about manipulations of symbols. And this is because if you keep meaning inside, you can use meaning to create paradoxes. And then if you have paradoxes, of course, your logical system becomes shaky. And the way the mathematicians solve this is to just remove the meaning and just talk about symbols. Right? Of course, something that only knows about the formal structure of meaningless symbols cannot really be used as a foundation for physics. So the view that we have in our head is that for physics, we have to start with physics. We have to start with things and models and idealization of what are the things around that we study with physics. And that way the semantics is really clear, because it's clear that it's coming from our experiment setups, our abstraction about the world, and so on. And then from physics, we are going to take some physical requirements so that in certain conditions, we're going to be able to assume that some things behave in a particular way. And then we take those things. The goal is then to write that down really clearly, formally. And then from that, construct the mathematics that is those meaningless symbols according to the rules that are given to us from the physics. And we call this physical mathematics in contrast with the other, because we're starting from the physics, we're starting with clear physical requirements and spelling them out and constructing the mathematical structure. And a lot of the things that we have in physical mathematics are kind of like proofs in the sense that 200 years ago they may have been considered proofs because back then mathematics was not purely this game of abstract symbols, but now they're not. We can't call them proofs anymore, so we call them justifications. So the idea is going to be to find some sort of tight logical reasoning such that these physical objects can be formalized with these mathematical objects with that structure. So that's in a nutshell the idea. So really, again, to reiterate this division is that the physics really lives in an informal world where you have these concepts that have meaning, that they reference to each other, right? And that part really cannot be defined in terms of the formal system, but then we sort of bring in the formal system through assumptions and definition some sort of idealized version of the objects, and those are the mathematical objects on which you construct the formal theory. And again, the map between the informal and formal system is the most important and delicate step, and it's kind of the least studied, because a lot of the time, even people who do theoretical physicists, they look at the mathematical structure, but the mathematical structure, is here after this process of idealization. So all the interesting bits of what is the system, why should be characterized like this, are in this transition. So they live essentially across this informal and formal world. And once you are in the formal world, you already have defined everything. So there is no more physics. Like if you know exactly what happened during these steps, like what are the things that you're bringing in the formal system and why and how, that's all the physics, because all the rest is again manipulation of symbols according to some rules, and so you're not adding anything more than what's already was there in the structure. So just to give you an example of like how we should work and think about this thing, let's just start with classical mechanics, because again it's one of the things that we have the biggest idea of, right? So if you have Hamiltonian mechanics, then Hamiltonian mechanics is a phase space plus some Hamiltonian evolution, and so the phase space is mathematically a symplectic manifold, and the Hamiltonian evolution is an additional structure on the symplectic manifold that represents that captures the physical idea of determining reversibility. But mathematically, the symplectic manifold is two things. It's a differentiable manifold plus a symplectic structure. And the idea is that this structure is there to be able to define observer-independent count of states. So all of this structure is there to capture this physical idea. But a differentiable manifold is also not a prime structure, is a manifold with a differentiable structure. And again, what is this differentiable structure? Well, that is there so that we can, under the assumption of infinitesimal reducibility, we can take parts and parts and parts and parts, and we can still talk about the infinitesimal. And that's what gives us a differentiable structure. And a manifold is also not a prime structure, is a topological space locally isomorphic to Rn. And the idea of this locally isomorphic to Rn is because it's identified by an independent continuous, a set of independent continuous quantities, and the fact it's a topological space comes from the idea that the points of the space are experimental distributional cases that are distinguishable with verifiable statements. So again, in this whole structure, we can know each part of the mathematical structure that we're layering on top, where it's coming from and how it's physically justified, and what are the physical characteristics that we're going to capture. So the idea would be to have all of the mathematics that we need done this in a very tight way so that we can actually rederive everything. Another example is the idea of a probability space. A probability space mathematically is three things: is a set of points, a sigma algebra on those points, and a measure. And the set of points are again the experimental distinguishable cases in the same way that we had the topological space. The sigma algebra is are the statements that are actually associated with an experimental test. And then the measure is the probability that that particular statement is going to be found to be true through the test. And so again, this is a very tight justification from these, of this abstract structure from physical requirements. So this is the idea. This is what we like to have. And so now let's look at some of the details. Where again, there are going to be some parts that we have finished doing and some parts that we still have no idea how to do. So the general idea is to develop this general theory, and the first layer, starting from scratch, is this notion of experimental verifiability. And this is again fairly well done. It's in our book, and it's in the part of physical mathematics. The first three chapters are basically there to establish this layer. The idea here is really to find the logic of experimental verifiability. What does it mean? It means that the basic currents in our system is the idea of a verifiable statement, a statement that you can find that has an associated test, and the test finishes successfully in finite time if and only if the statement is true. So if we have a statement is equal to true, then the test result has to be success. In the case that the statement is false, the test might fail in finite time, or the result might be undefined because it never terminates, because it's really not defined, and so on. So the only condition is that there is the success is equal to true. Now what happens, and is that if we look at the logic of this statement, you can already see that you're not going to have the negation, because if you do a negation and you try to invert success and failure, your undefined part will go in terms of the truth. So there is no guarantee that the process is actually going to terminate successfully infinite time if the statement is true. So the logic of experimental verifiability, the logic of verifiable statement, does not have negation. What it does have is the finite conjunction, the finite logical end, because in that case we just need to check that all the statements terminate, and since there are finitely many of them, all terminate in finite time, the test will terminate in finite time. So the logical end, the finite conjunction of verifiable statement, is guaranteed to be verifiable, to be a verifiable statement itself. Now, if you had infinitely many, of course, you would not be able to guarantee the determination in finite time, and so you do not have the infinite conjunction, but you do have the infinite disjunction, because you only need to find one statement that terminates successfully, and then if that statement is true, you can quit your procedure and the countable conjunction is disjunction is verified. It has to be countable because you need to be able to find that statement, and so you can only find one statement through countably many. And so the idea is that if we want physical theories to be evidence-based, then all the theoretical statements in the theory must be associated with the test. You must have something that is constructed from those set of verifiable statements that you have. And the idea is that this, once you work out the details of this framework, you find that there is a connection between this logic of experimental verifiability and topologies and sigma algebra. And mathematicians will know what topologies and sigma algebra are. To physicists, they are really low-level structure on which everything else is built upon. So again, all of differential geometry is built on top of topology, and measure theory, so theories of integration, probability theory, information theory, are built on sigma algebra. And so the idea is this is how the parallel work, is that the set of points on our space are going to be the set of what we call possibility, the cases that can be distinguished experimentally, that are defined from the set of verifiable statements. The verifiable statements corresponds to open sets, and the theoretical statements correspond to the Borel sigma algebra, the Borel sets. And so you can find really a one-to-one map between all these things, such that you can go and reread every mathematical proof in terms of this idea of finite determination and tests and so on. This also gives an idea why functions in physics they must be well-behaved. And again, this well-behavedness comes from the idea that if I have a verifiable statement, that it's connected to another statement, and I can verify this, and I know that when this is true, the other one is true, then the second one also is a verifiable statement, because we can make the inference between verifiable statements, and this forces all physically meaningful maps to be topologically continuous. And when you do have analytical discontinuity in physics, for example, when you have phase transitions, some things are going to change discontinuously. This analytically discontinuity is actually on that boundary, something happens in terms of experimental distinguishability, because while we can't know exactly on which point we are in each phase, we can know, for example, that we are in the triple point. We can verify, yes, we are in the triple point, and that's why the triple point was used as a starting point for our unit system, right? We can verify that. And so topologically, that point is isolated, and so you can be topologically discontinuous there, even though analytically you're going to be discontinuous. So as I said, a lot of things sort of make sense from the tiny little detail of math to the sort of general ideas in physics, and this is the type of map that we'd like to have. And I'll probably create this year a series of videos on this topic, because it's really fascinating how the math and the physics can actually go so well hand in hand with these structures. And everything that we then define on top of this is the idea of quantities and ordering. And what we create, what we find is a set of necessary and sufficient conditions such that a set of verifiable statements basically describe a continuous quantity. And again, we do this not really abstractly with abstract notion mathematics that come out of nowhere. The idea is to have a modernization of something that we do operationally. And so, for every quantity that we measure, like we have an idea of reference, like the tick of the clocks, the mark on a ruler, and these references are going to be able to distinguish a before and an after. So the statement, the object is before the reference or it's after the reference, those are verifiable statements. And the idea is that we can reconstruct the real numbers, essentially by having requirements on these references. You need to have enough references, you need to be able to make them small enough, they have to have some sort of logical relationship between them, and you're going to be able to show exactly what are physically the conditions that you need. And what's very interesting that comes from this type of work is that the assumptions that are really hard, the ones that do most of the work, are not really recovering the real numbers, are recovering the idea of an ordered quantity. And none of those ideas of ordered quantities, right, are tenable assumption at Planck length, right? So at some point, those assumptions fail because they're untenable. And so the idea is that what this tells us is that when we're going to go and have some physics at that scale, we really are not going to have an idea of ordered time anymore. We're going to have something that it's fuzzier because there is no way to consistently order things. There is no objective before or after, right? So this is again part of the work, and we have absolutely no idea of what would be the correct structure, except that we know that we would have some topological structure, and there are some features that this topological structure has to have. So, but this is again one of the powerful way of this approach is that by layering out all the assumptions one by one, you know the realm of applicability, so you know what needs to fail if you're going outside of those assumptions. Now, the second layer of serial mathematics is a lot less well developed, and it's essentially the idea of giving a notion of let's say accuracy of how fine the description is in each measurement. So in its verifiable statement. So we saw before that logical relationships are the purview of topology sigma algebra. So if I say that the position of an object is between 0 and 1 meter, this is a narrower statement than the position of the object is between 0 and 1 kilometers. And narrower means really that the statement is contained in 1 another. So all the topology knows about the structure and continuity knows about the structure. But there are other structures, like the ones that we have in geometry, that have to know more. And the idea for us is that the relationship of granularity of statements should be enough to cover all those cases. Because if I say that the position of the object is between 0 and 1 meters, or that the position of the object is between 2 and 3 kilometers, right? This statement is not contained in this, but I know that this is more refined than this because the position is smaller. So it gives us more information knowing that the object is in a smaller range than a bigger range. In the same way, if I say that the fair die is landed on 1, this gives us more information than saying that the fair die landed on 3 or 4. And again, these are sort of probabilistic statements, and so this makes it that the finer statement, the one that has more that is more reliable, more information, is the one that has less chance of happening. And similarly, if I say that the first bit is 0 and the second bit is 1, this gives us more information than just saying that the third bit is 0. And again, this is essentially the same type of structure that it's for the other. So ideally, if we just have this one operation that tells us this statement gives us more information than the other, all the geometry, probability, information should be able to come from this single structure. And so we would have a single unified structure for all these ideas. And everything that this structure should be able to distinguish is between statements that are on different units, essentially. So if I have a single point in phase space, the statement A that corresponds to a single point is finer than the statement B that corresponds to 2 points, and it's also finer than the statement C, which is a one-dimensional set of points, which is also finer than the set E, right? So we can compare these 3 statements in terms of this granularity. Some of them have more information than the other, but the statements between, we cannot compare C and D because a range in position and a range in momentum are incommensurable. We can't say that one is bigger than the other. So one of the ideas is that not only this notion of granularity should be able to model all these different structures, it might also be able to tell us something about, capture mathematically what physical dimension and units are. And so the idea is that in this theoretical domain, you pick a statement and then you want to construct a measure based on that statement, such that that statement is equal to 1. And if one statement is finer than another, then the measure is smaller. And so you take one statement, that's your unit statement of 1 meter, and then there are things that are smaller than a meter, bigger than a meter, and so on. So this is more or less what we started writing out. And again, it seems that the correct mathematics for doing these sort of things, at least we are not aware that it exists. We talked to some other people in the math world, and they don't seem to be aware that this exists. So there might be new mathematics here to discover. And everything that if we wanted to impose some structure like this in quantum mechanics, there seems to be a little bit of a twist in terms of that these measure that we put on states across quantum context is not going to be additive. And one of the ways that we can see this, and this is something that we are starting more actively to actually look at this detail, is that in between statistical mechanics and measure theory, there is, at least in classical mechanics, there is the idea that if we have a uniform distribution, the entropy of the uniform distribution is the logarithm of the count to state. This is sort of one of the assumptions in statistical mechanics. Now, in quantum mechanics, you do not really have something like that. And so the idea is that you don't really have already provided a count of states because this thing is not defined. And so we thought, well, what if, since this part is well defined with the von Neumann entropy, what if we created this count of states, defined the count of states from for the von Neumann entropy? And what you find is, again, this interesting hybrid between essentially classical, discrete, and continuum with respect to quantum mechanics. Because if you are in a classical discrete case, you would use a counting measure, and therefore each point would have measure 1, and each set with a continuous range would have measure infinity. If you would using the Lebesgue measure, right, like you would say on a continuum for like meters, seconds, and so on, a finite continuous range would have a finite number, like a finite measure, like 3 meters, 4 meters, and so on, while a single point would have measure 0, right? If we have a single point in space, that there is no length associated with it. What we find in quantum mechanics, if we create this quantum measure, you find that a single point will have will correspond to one state, which means 0 entropy. But then if you create a finite continuous range, you will find that this is also finite, right? So you see that these basically have they work like in the discrete for the single point, but they work like the continuous with a finite continuous range. And so the interesting thing here is that ideally, if we had a measure to count states, right, we would like this measure to give us 1 for every single point, to give us a finite number for finite ranges, because finite ranges should carry finite information. And we would like the measure to be additive for disjoint set. If we have two sets that are disjoint, the total number of states is the states in this set plus the states of this set. And the point is that these three things are incompatible with each other, and they correspond. So you have to sacrifice one of these three. And these three cases, they all sacrifice one. So in the first case, we have that single point counts as one, and the measure is additive, but the finite continuous range is not a finite measure. In the Lebesgue measure, we have a single point is not one, is zero, but you have finite ranges, finite measure on finite ranges, and the measure is additive. And in quantum mechanics, instead, you sacrifice additivity, and you have the one and the second. And so the idea is that we want to really understand exactly how this works, and for these first two cases, that are classical cases, there is an idea that those measures are essentially unique up to some scalar quantity. And the idea is, if we were able to show that there is only one way to create these quantities measured, then again it would give us a little bit more insight in the structure of quantum mechanics. Now, differentiability is another structure that we need to recover, and we said is based on top of manifolds and on top of topological spaces. And we would like to have this created from physical idea for music understanding. And one thing that people may not know, coming from the physics world, is that there isn't just one theory of integration or of differentiation. There are many of them, and so the question is, which one is the one that we are interested in? And just to give you some sort of idea of why some of the ones that we have are not really exactly what we want in physics, let's take, for example, what we have in terms of differential topology and differential geometry, right? So the idea is that in those contexts, you define a differentiable manifold as a manifold that is something that can be charted, that can be identified with continuous quantities, plus a differentiable structure. And in the differentiable structure, right, you basically are asking that all changes of coordinate are differentiable, so that you always, the derivatives from one coordinate to the other, they always exist, and it's well defined. Now, this idea of differentiable structure then is defined on top of the standard Frechet derivative. This is the standard derivatives that you have on Rn. But then what happens is that you define objects on top, you define vectors as being a derivation of scalar functions. So a vector now is something that takes a scalar function and returns another scalar function that is going to be the directional derivative. And the partial derivatives essentially become the basis of the vectors, like the vector basis, right? Because all vectors now are derivatives. And differentials are defined as linear functions of vectors. So they take one of these objects and they give you a number. And so dx would be one of these differential, and it takes a vector v, which is again is a differentiation, and then it would give you the component v on the x coordinate. And then the integrals are defined on top of these differential forms. And so delta x is going to be the integral of dx, where again dx is this map. Right? The issue with this is that this is not really physically does not make sense. Like it's not, it does not have the correct physical feature for us to be able to derive the structure. Why? First of all, velocity is not a derivation, right? Velocity is a change of position, right? That's how we have it in our head. It's not something that takes a function and gives us back the function. And the mathematician is going to say, oh yeah, but it's isomorphic to this and that. Yeah, but it's not what we need, right? It's the fact that this symbol has some similar property to something else. It's irrelevant. We need to be able to define things that are coming from physical idea. Then momentum, by the same token, is not a function of derivation. It's just a set of variables that we use to identify a state. That's what it is. The other issue is that the derivation depends on the units and can't be summed. So if we are in spherical coordinate, right, and we have r and theta, the basis vector would be partial r, partial theta. These things cannot be summed, right, because they are units. And so they are not even part physically of the same vector space. There's something different. Then the other thing that I don't particularly like is that you have really two notions of differentials. You have the notion that is defined here in the differentiable structure when you are defining the partial derivatives of the coordinates, and then you have another differential on top. And why do we have two things? Like we would like to have one. And then the other things that sort of implies is that the infinitesimal objects are not constructed as limit of finite objects, right? And so here we define the differential, right? And then we integrate. It's the delta x is defined as an integration of dx, right? And it's really what we would like to have is the opposite, like the dx is the infinitesimal limit of something finite. Because even though those are like older thinking in mathematics, those are the things that we need in physics. And so it's not necessarily true that when mathematicians makes generalization and gives us this abstract structure, they are the things that we actually need in physics. And so, for example, one of the things that we'd like to do, it would be to have a physically motivated idea of differentiability, then again with from this idea of infinitesimal reducibility. We have something and then make it we take parts, and we take parts, and this limit is going to exist. And so what we'd like to have is an idea of a differential that is basically constructed from a limit of a sequence in any vector space. And the idea is that once we have this definition of differential in terms of limits on a vector space, we can use it for any vector space. So even the infinitesimal surface change, right, the infinitesimal surface change will be limits in some vector space as well. And so the idea is that we can use one idea of differential and for everything. And so, for example, we would have, the idea of time, space, and temperature, and we would have a trajectory that gives us space as a function of time, and we have a temperature function that gives us temperature in terms of space. And the idea is that we have the differential for all of these, which are basically these infinitesimal changes, and then the derivatives are just the maps between these infinitesimal changes. So this part, these derivatives, can really be understood as a map from a differential to another differential. And this idea also works for more complicated objects. And it also gives us sort of the correct chain rules that we would like to have. And so the goal, again, would be to find other people in math that helps us develop this so that we can sort of dress it up and make the mathematical objects really one-to-one to these elements in the same way that we did it for topologies and sigma algebras. Inside differential geometry, there are these notions of forms and linear functional, which is, again, for us, it's like defining derivatives on surfaces of different dimensions. And again, the idea for us is not to start from the infinitesimal and integrate like they do in math, is to start from the idea that we have finite things measured on finite area. So for example, for mass, we never measure the mass density, right? That's not something that is prime in physics. So what we measure is a finite amount of mass over a finite volume. And then we assume that the mass is additive. If we have two disjoint volumes, then the total mass is the mass in the two disjoint region. And then the idea is that we can do this decomposition over and over and over until we have these infinitesimal pieces. And so the mass density is really the infinitesimal mass in an infinitesimal region. By the same token, the magnetic field is not something that we measure exactly at a point, right? We measure magnetic flux going through a surface, and the magnetic field is going to be the infinitesimal magnetic flux within the infinitesimal surface. Work is something that we measure. The force at a particular point, that's not something that we measure. Again, the force is going to be the infinitesimal amount of work with the infinitesimal displacement. So the idea is really to construct all these objects from this idea of starting with finite object and making the finite one in the same way that we constructed the real number coming from references and so on. And the goal is to essentially be able to re-understand the Stokes theorem and all these other great stuff that is in differentiable calculus as the properties of the finite elements. And we have sort of proof of concept that this can be done, and it gives us a lot more physical insight. And not only it tells us what happens, what physical assumption we are going to put in, and what happens when those physical assumptions fail. So how differentiability, for example, is going to break down once we find that on Planck scale things are not as additive as we thought that they should be, or we assume them to be in this context. So this was an idea of like all those mathematical structure. Now the other thing that we would like to have is a common structure for states and processes. This is something that we are still sort of actively worked on. So I don't know how much I can actually write here, because probably in 3 months this stuff is going to be old anyway. So just give you a very abstract view is again, as we said before, we want to start with the notion of states as ensembles, because again the idea is that whenever we write the laws of physics, we're never really specifying a particular case. We are essentially finding relationship between preparation procedure and measurement procedure. Like every time that we prepare something with these features, we measure something with this feature, right? So it's this every time that already leads you conceptually to the notion of ensemble. Ensemble form a convex space because you can always take two and then make a linear combination of them with probability, and there are some properties that this ensemble space needs to be satisfy, and this will give us a notion of a convex space. And everything that ensembles needs to be able to give us is a notion of entropy, and again there are some conditions that an entropy needs to satisfy. And we are still trying to understand what is a set of constraints that we can put on a generic state space such that it will recover the Gibbs entropy for classical mechanics and the von Neumann entropy for quantum mechanics. These are still things that we are still trying to look at. But one of the things that is interesting to us is that it's very clear that the entropic structure is the one that is responsible for all geometric structure in classical mechanics, quantum mechanics, statistical mechanics, everywhere. And there is a nice link between the physical entropy and that structure in terms of what is called the Jensen-Shannon divergence. And the idea is simply to take two states, make an equal mixture of them, and see how the entropy goes up with respect to the average entropy of the two. Right? So if the two states are the same, then the entropy is not going to go up, and you're going to have zero if and only if ρ1 and ρ2 are the same. And if ρ1 and ρ2 are completely distinct, they basically have their distribution that with disjoint support, then you're going to have the increased entropy is exactly 1. And it turns out that this quantity, right, it's the square of a distance function, and it's the square of the distance function that it's recovered by the Fisher-Rao metric. So there is really a lot of relationship between geometry, physical entropy, information theory type entropy that needs to be understood. And as I said, like we are still sort of in the phase of gathering up all these ideas. So that's basically it. I think it's probably enough. So the four things that I hope at least you got is that we have a different approach to the foundations of physics. We don't have an interpretation. We're not interested in interpretation or theory of everything. We really want physically meaningful starting points from which we can derive the laws and the mathematical framework they need. We have two approaches. One is, let's say, top-down from the physical, to reverse engineer the principle from the non-laws. We call this reverse physics. The work on classical mechanics is done. We have very good idea for both thermodynamics and quantum mechanics. We just need to do it. And we still don't know how to generalize to field theory because there are really mathematical issues there that need to be figured out. And then we have another approach that it's bottom-up, which we call the physical mathematics, and really the goal is to derive the mathematical structure from scratch, layering out axioms and definition one by one with appropriate physical justification. And again, there, topology and simple algebra are derived from experimental verifiability. That part is basically done. It maybe could be improved, but it's basically done. There is a measure theory level that should connect to informational granularity. That's how we call it, so how much information each statement carry. That part still needs major work. There are pieces of math that are really, really missing that needs to be developed. And then we also have an idea of, inside that same layer, differentiability. We at least have a good idea of how to get that to work once measures are done. And then we also started to formalize a general notion of state and processes. There is some literature there that we can use. There are some parts that needs to be developed and so on. And again, so the goal is very ambitious and requires a wide collaboration. So we are trying to find as many physicists, mathematicians, philosophers to collaborate on. So if you're a student from the University of Michigan, you want to collaborate and help us out, come and contact me. And also if you are another researcher somewhere and you can say, oh, maybe I have this piece that might help you to do something else, please do contact me as well. And again, thank you for the attention. And if you are interested in some parts, you can also leave a comment and I'll try to answer. Thanks. Bye.